You know, in the world of high-tech manufacturing, precision is absolutely everything. But what if the biggest threat to all that precision is something you can't even see? We're going to talk about a tiny, invisible flaw that can cause catastrophic failure in some of the most advanced machines on the planet. So in this explainer, we're going to dig into what it is and how engineers are fighting back.
Okay, so take a look at this. What you're looking at is a high-performance clutch housing, a supercritical part of a car's transmission. This thing is built to handle an insane amount of force. But see those tiny little pits on the surface? They're really just the tip of the iceberg. Underneath, there are these microscopic holes, or pores, that can cause the whole part to just crack and fail while you're driving. And figuring out how to get rid of these is honestly one of the biggest challenges in modern manufacturing.
Right, so before we even get into the solutions, we gotta understand the enemy. What exactly are these tiny holes, and where in the world do they come from?
All right, first up, diagnosing the defect. In the world of high-pressure die casting, you really have to know your enemy. Because if you try to fix the wrong problem, well, you can actually make things a whole lot worse.
So at its core, these little holes come in two main flavors. First, you've got what's called gas porosity. The easiest way to think about this is like bubbles of gas getting trapped inside the liquid metal as it solidifies. Then you have shrinkage porosity. This one happens when the metal itself shrinks as it cools down, and if there isn't enough liquid metal to fill that gap, it just leaves an empty space behind.
And this is where it gets really interesting. Engineers can actually tell the difference just by looking at the hole under a microscope. A gas pore, it's usually round, and it has a smooth, shiny inner wall. It's basically a fossilized bubble. A shrinkage pore, on the other hand, is irregular, almost like a jagged tear in the metal, with a rough crystalline surface. And that tells an engineer a completely different story about what went wrong in the process.
Okay, so the battle against these flaws, it actually starts way before the metal even sees the inside of a mold. It all begins with creating the perfect, ultra-pure molten aluminum.
See, the thing is, molten aluminum is kind of like a sponge for hydrogen gas and all these other tiny impurities. And those impurities, they act like little seeds for these flaws to grow. So to stop them before they start, engineers go through this incredibly meticulous purification process. They bubble argon gas through the liquid to pull out all that hydrogen, they put strict limits on contaminants, they try to avoid using too much scrap metal, and they preheat everything to bake off any moisture. The end goal is super simple. Make that metal as clean as humanly possible.
Okay, so we've got our super pure metal ready to go. Now we get to the real heart of the process, mastering the flow. This is where that molten metal gets injected into the mold at incredible speed and pressure, and it all happens in literally the blink of an eye. This is just a fantastic example of process control. On the left, that's the old way. See how they're blasting the metal in too fast, too early? It just splashes and tumbles in there, trapping air all over the place. But on the right, wow, the engineers made this tiny but absolutely brilliant adjustment. They delayed the start of that high-speed blast by just a few milliseconds. This lets the metal flow in smoothly at first, pushing the air out ahead of it right before that final, powerful injection fills the mold completely. And then comes the final punch. After the mold is totally full, a massive pressure is applied. We're talking 90 megapascals. To give you an idea of how much that is, it's like stacking a couple of cars on something the size of your thumbnail. It's just immense. And that final squeeze is designed to crush any tiny little voids that might be left, making the final part incredibly dense and strong.
But here's the thing. You could have the most perfect metal and the most perfect injection timing, but if your mold temperature is off, you're still going to have problems. Think about it. If that steel mold is too cold, the second the hot aluminum touches it, that outer layer just freezes instantly. This can trap gas right near the surface and cause all sorts of other defects. So the mold itself has to be preheated to a really precise, stable temperature to make sure everything solidifies just right.
Okay, but what about the really critical components? I'm talking about aerospace parts, or maybe the big structural frames for high-performance EVs. For that stuff, engineers need an even more powerful weapon in their toolbox.
And the logic behind this next step is so simple, it's brilliant. I mean, if trapped gas is the enemy, why not just get rid of the gas in the first place? And that's the whole idea behind vacuum-assisted die casting. Right before the metal is injected, a powerful pump just sucks nearly all of the air out of the mold, creating a vacuum. And the results? Oh, they're an absolute game changer. By getting rid of the air, it slashes gas porosity by more than 80%. It also lets the metal fill these incredibly thin, complex shapes that would be impossible otherwise. And maybe most importantly, you get parts that are so dense and so pure that you can heat treat them to be as strong as forged parts. That's huge.
So where does all this amazing tech lead us? Well, it's taking us right to the future. The quest for what they call zero-defect casting.
an era driven by data and a relentless hunt for perfection.
So yeah, the ultimate goal here is zero-defect manufacturing, perfection. And to get there, the industry is using some seriously cool tools, like industrial CT scanners that can basically see inside a finished part and map out every single microscopic flaw. All that data gets fed right back into the system, with real-time sensors making constant little adjustments, all in the chase for flawless complexity every single time.
So if there's one thing to take away from all this, it's that there's no single magic bullet here. Making those high-quality, lightweight metal parts we all rely on every day, it takes a super deep understanding of physics and this multi-layered strategy to control literally every single variable in the process, from the purity of the raw aluminum all the way down to the final microsecond of pressure.
You know, it's this constant, systematic battle against these invisible little flaws that really pushes technology forward. Because as we demand parts that are lighter, stronger, and more complex for everything from our cars to our phones, the real question is, how close can we actually get to absolute perfection? And that quest is what's constantly going to redefine what's even possible.